Today, we are diving into the invisible world that powers pretty much everything, electric potential. Now, the best way to think about it is as an energy landscape, a hidden terrain of hills and valleys that tells every single electric charge where to go and what to do. It's the secret architecture behind it all.
So here's what we're going to cover. We'll start with that energy landscape idea to get a good feel for it. Then, we'll look at what this landscape is like around a single charge, connect it all to energy and work, and see how the steepness of the landscape actually creates a force. After that, we'll jump into some real-world problems and finish up with some key exam questions.
All right, first up, let's get a feel for this terrain of energy and figure out what electric potential actually is. Okay, so here's the formal textbook definition. It's the work done per unit positive charge to bring a charge from infinity to a point. The keywords you really want to grab onto are work done and per unit charge. See, this isn't about the total energy. It's more like the energy cost per coulomb to put a charge at that one specific spot.
This right here gets to the heart of it. Imagine you have two positive charges. They naturally push each other away, right? So if you try to force them closer, you're fighting against that repulsion. You have to do work, kind of like pushing a ball up a hill. And the work you put in, it gets stored as energy. In our world, that's electric potential energy. The potential went up because you did work against the field.
And this whole idea lines up perfectly with something we already get, gravity. With gravity, an object's height determines its potential energy. Well, in the electric world, potential is just the electrical height. A point with a high potential is like being at the top of a very tall hill on our energy map. It's a spot with a lot more stored energy per charge.
So, what does this energy landscape actually look like? Let's zoom right in on a single lonely charge and see the kinds of hills and wells it creates around itself.
This is the formula we need. It tells us the potential V at some distance r away from a source charge Q. And don't worry about that little epsilon naught symbol. It's just a constant, a number that makes the units work out. The big takeaway here is simple. The potential just depends on the charge creating the field, Q, and how far away you are from it, R.
And check this out. This is where that whole landscape metaphor just clicks. A positive charge creates a potential hill. Any other positive charge brought near it will naturally want to roll down and away. But a negative charge? It does the opposite. It creates a potential well that positive charges will naturally fall into. If you can picture this, you can predict how charges are going to move.
Okay, so now that we can actually visualize this landscape, let's talk about the energy it costs to move a charge around in it.
And here's the piece that ties it all together. If potential, V, is the energy per charge at a spot, then the total potential energy, U, that a specific charge actually has, is just its own charge, Q, multiplied by that potential. It's like knowing the height of a mountain is one thing, but calculating the actual potential energy of a specific hiker standing on it is another.
Okay, this is absolutely crucial to get right. Electric potential, in volts, is a property of a location. The potential exists at a point in space whether there's a charge there or not. Electric potential energy, in joules, is the energy a specific charge has because it's at that location. One is the landscape, the other is the thing on the landscape.
And this all boils down to a really simple and powerful idea. The work you need to do to move a charge from one point to another is just the charge Q times the change in potential, which we call delta V. It's just like how lifting a box depends on its mass and how much you change its height. Same idea here.
Next up, let's connect the shape of our energy landscape to the actual force a charge feels. How does the steepness of the hill create a real push or pull?
So let's just ask it directly. If potential is the height of the landscape, what part of it determines the force that's pushing a charge? How are the electric field and this potential landscape actually related?
The answer is the gradient. Or, to put it simply, the steepness. The electric field strength, E, is the negative of the potential gradient. That means the faster the potential changes over a distance, the steeper the hill, the stronger the electric field is at that spot. A really steep potential hill means a really strong push.
Think about the space between two parallel charged plates. In there, the electric field is uniform, it's the same everywhere. So the potential landscape is a perfectly straight, even slope. Since the steepness never changes, the potential gradient is constant. And that tells you the electric field strength is exactly the same everywhere between those plates.
But for a point charge, that potential hill was a curve, remember? The steepness is always changing depending on how close you are. So to find the field strength at one specific point, we can't just do a simple division. We have to find the gradient of the curve at that exact spot. And we do that by drawing a tangent line to the curve and finding its slope.
The steeper that tangent is, the stronger the field is right there.
Okay, theory is one thing, but let's put this into practice. We're going to walk through a couple of examples to see exactly how you apply these formulas and ideas to solve real problems.
All right, here's our first problem. We've got two spots in space, A and B. We know their potentials. First, we need to find the potential difference between them, and then figure out how much work it would take to move a single proton from the low point, B, to the high point, A.
Let's break it down. First, the potential difference. We're going from B to A, so the final potential is VA, and the initial is VB. That's 450 volts minus a negative 150 volts, so the total climb is 600 volts. Simple enough. Now, for the work done, we just use our formula. W equals Q times delta V. We plug in the charge of a proton, multiply it by that 600-volt difference, and we get 9.6 times 10 to the minus 17 joules. It's an incredibly tiny amount of energy, sure, but it perfectly follows the rules of our landscape.
Okay, let's try something a little more involved. Now we have two source charges, and they're creating a combined potential landscape. Our job is to figure out the work needed to move a tiny test charge from the exact middle point to a new spot, a bit closer to one of the main charges.
Whenever you see a problem that looks complicated like this, the trick is just to break it down into smaller, easier steps. First, we'll find the potential at the starting point. Second, we'll find the potential at the end point. Third, we'll calculate the difference between them. And fourth, we'll use our work formula to get the final answer.
So, let's do it. Step 1, the initial potential. At the midpoint, it's the same distance from both charges, so we can calculate the potential from 1 and just double it. That gives us an initial potential of 2.7 million volts. Whoa! Step 2, the final potential. Now our little charge is closer to one source and farther from the other. We have to calculate the potential from each one separately and add them up. That gives us an even higher potential of 3.6 million volts. Step 3, what's the change? Final minus initial. That's a climb of 0.9 million volts. And finally, step 4, work equals Q times delta V. We multiply that huge potential change by our tiny little test charge, and we get our work done.
And there it is. The final result of all that math is 0.45 joules. That's how much work it takes to push that small charge up the combined potential hill from those two bigger charges. All right, to finish up, let's run through a few essential questions, the kind you might see on a test. This is a great way to make sure these key ideas are really locked in.
First one, and it takes us right back to the beginning. How do you properly and fully define electric potential?
So a complete answer has to have these parts. It's the work done per unit positive charge. You have to mention that you're moving it from a reference point of infinity, which is our zero level. And here's a key detail. You're doing it without changing its kinetic energy. No speeding up. It's all about the change in potential. Okay, next question. Think back to that uniform field between two plates, and remember that straight slope on the graph. How does the potential change as you move from one plate to the other? It's a straight line. The potential varies linearly. It starts at 0 volts on the grounded plate and climbs steadily and predictably until it hits its maximum, V0, at the positive plate. And that perfect linear relationship is the dead giveaway that you're dealing with a uniform electric field.
And for our last review question, let's connect the two big ideas, the field strength, E, and the potential. How are they related?
The relationship is simple and direct. The electric field strength is the negative of the potential gradient. And that little negative sign is so important. All it means is that the electric field, the force, always points downhill on our energy landscape. It always points from a place of higher potential to a place of lower potential.
So I'll leave you with one final thought to chew on. We've talked all about this energy landscape, but what is it that actually determines if a charge will naturally roll downhill? And how does this one invisible concept shape everything, from the chemistry happening inside a battery to the epic dance of particles in the vastness of space? Thanks for watching.